So I'm getting 0.1044 molar HCl. Pretty dang close to the 0.1 that I thought, but a little bit elevated, and we've already listed some reasons for why that could be true. Let's pause though and think about how many sig figs I am allowed to get. We've already discussed that my burette there allows me to go out to 2 decimal places, which would get me, as you can see here in our measurement of volume of base, 4 sig figs. And so I have 4 sig figs here in this calculation, but in reality I should have rounded this to 2 sig figs, because right here, let's look at this. This is moles per liter of sodium hydroxide. That information is reported on the bottle of sodium hydroxide that I used, which means that whoever made that sodium hydroxide was only confident out to 2 sig figs. So if they were only confident out to 2 sig figs, and I used their chemical in my burette, I can only be confident out to 2 sig figs. So in reality, 0.1 molar HCl. Okay, so real quick, I know there's kind of a glare, but I think you can see this. Just a real quick review. You know, this is what the titration curve for this exact titration would have looked like. As we slowly added some sodium hydroxide, the pH would climb, and then very near the equivalence point, we would get this vertical inflection, and it would start to climb rapidly. You guys know that strong titrations, their pH curves are characterized by the fact that this vertical region is very tall, and that at the equivalence point, which is always halfway through that vertical region, the pH is exactly 7. Again, why is that true? Because the sodium hydroxide, the hydroxide ions would have perfectly, completely reacted away all of the H pluses from the acid in my flask, meaning that at that point I would just have salt and water, perfectly neutral. However, if we do a weak strong titration, which we're about to do, you will see, and I can show with my pH meter, that the pH at the equivalence point is going to be above 7. We are about to do a titration using the exact same titrant, sodium hydroxide, the exact same concentration, 0.1 molar, but this time we're going to use a different acid. We're going to use acetic acid, which you probably know as vinegar. And I actually have 0.1 molar acetic acid. So, what is going to be true about the equivalence point of my weak strong titration compared to the equivalence point of my strong titration? I'm using the exact same concentrations, exact same amounts, so what's going to be true? Well, the equivalence point should occur at the same location, at the same x-coordinate on this graph with the same volume of sodium hydroxide titrant added, because remember, the equivalence point is stoichiometry. When we are analyzing equivalence points, the question is how many moles of each reactant do you have? It's a reaction that goes to completion. With a strong titration, it's a perfect neutralization reaction. With a weak strong titration, it's a proton transfer reaction. Both of those go to completion. We analyze reactions that go to completion with stoichiometry, right? So, how much strong base I have to add does not depend at all upon the strength of the acid. It just depends on the concentration and how much I have. It depends on the number of moles that I have of that acid floating around. So here's just a real quick reminder for you of the 2 different things that are happening whenever we do a strong or a weak titration. So here's what's happening with a strong acid, strong base titration. I'm slowly adding, in that last titration, I was slowly adding hydroxide ions up until the point when these were present in stoichiometrically equivalent amounts. And then all I had was water. The pH is 7. And then any hydroxide I add after that, I just have excess hydroxide floating around, so the hydroxide then would be dominating the pH. However, here, when I'm titrating a weak acid with a strong base, up until the equivalence point, this is the proton transfer reaction that goes to completion that dominates. So you know that at the equivalence point, these are present in equivalent amounts. They consume each other away. What do I have left over? Unlike last time when I just had water left over, this time I have the conjugate anion of my acid, which behaves as a base. And so that's why the pH at the equivalence point, when these have reacted completely away, consumed each other away because they're present in perfect stoichiometrically equivalent amounts, I have a base left. That's why the pH is greater than 7 for a weak acid strong base titration, right? And there's another important point for a weak acid strong base titration. Do you guys remember what it is? Yeah, it's the midpoint. At the midpoint, I have these present in a 2-to-1 ratio. So this is still limiting. This would still be my limiting reactant. It's always my limiting reactant up until the equivalence point. Past the equivalence point is present in excess. So when I have these present in a 2-to-1 ratio, this completely gets consumed away. Half of this gets consumed, and an equivalent amount of this gets consumed. So what do I end up with? I end up with equal concentrations of HA and A minus, which is a perfect buffer, right? I know I've gone over this and over this, but it is really important. For any weak, strong titration like this, up until the equivalence point, I'm going to have a significant amount of this weak acid, and because I'm adding those hydroxide ions, I end up reacting to create that conjugate base. So I have a weak acid conjugate base pair present in significant quantities. I have a buffer, and we know that we can analyze that through the Henderson-Hasselbalch equation, right? So what I was just saying, at the midpoint, this ratio is a 1. Log of 1 is 0. That drops out. pH equals pKa. So our task now is to take some acetic acid, which again you probably know is vinegar. Take some acetic acid and see if we can figure out what the Ka is. So if we can figure out the pKa, which should be the pH at the midpoint, then we should be able to figure out what the Ka is, what the acid dissociation constant of acetic acid is. And that is our goal for our next titration. Okay, so I have my titration set up once again. Sodium hydroxide here, my burette. My analyte is acetic acid. They both have the same concentration. I'm even using the same volumes as my strong titration. So I should be reaching the equivalence point once again at adding about 70 milliliters of base. Now, because I am really curious about what the Ka value of acetic acid is, that's the goal of me trying to do this titration, I want to be very careful to actually take pH data along several points of the titration, so I can actually construct a pH curve and analyze that pH curve to see if I can get the pKa from there. So I'm going to go about this very slowly and tediously. I'm going to add about 1 or 2 milliliters of sodium hydroxide, mark that as a data point, and then note the pH with my pH meter. So I'll get a coordinate point, and I can construct a pH curve of my own. Doing this, we should be able to see the midpoint. We should be able to see the equivalence point. I also have an indicator in here. You may notice, if you look very carefully, this is the tiniest little bit greenish yellow. I put an indicator in here called bromothymol blue, which is a little bit yellowy whenever something is very acidic, but as something becomes basic, it changes to blue. And it'll change to blue when I get near the equivalence point of this titration. So whenever this is a deep blue, I know that I'm at the equivalence point. Makes sense? So next time I see you, we'll have a nice little blue solution here, and I will have generated a pH curve, and then we can analyze that. Okay, so this is a little bit tricky to see, but this solution is very faintly blue, which tells me that I have reached and possibly surpassed the equivalence point. And remember, I was taking pH data for every about 2 milliliters of base I was adding, and I was able to generate a pretty good titration curve, a pretty good pH curve. So let's look at that curve that we got from running that titration. I tried to take a pH measurement about every 2 milliliters or so we got lots of good data. And you can see that it's pretty much just what we would expect for a weak acid strong base titration. It starts to, the pH starts to increase as I add my NaOH titrant, and then it levels off here. So I know the midpoint is somewhere around in here because this is an ideal buffer system. And then as I keep adding NaOH, my buffer system gets overwhelmed. And then right here, I have that classic vertical region where the equivalence point occurs. So right about in the middle of that vertical region is where I've reached equivalency. And then beyond that, I just have excess hydroxide ions causing the pH to grow. So, we know that the equivalence point occurs halfway through this little vertical region. And I really should have taken better data around here. I should have gotten more data points, but it's okay. So we know that for weak acid strong base titration, the pH at the equivalence point should be greater than 7, and we definitely are. It's around 8 or 9 is going to be the pH at the equivalence point. So remember, the whole point of this titration was to see if we could figure out what the Ka of acetic acid is, what the dissociation constant of acetic acid is. And we know that the pH equals the pKa at the midpoint. So I wonder if we can use our graph to discover what the midpoint was. Well, we can use this vertical region to try to discover what the equivalence point was, and then take half of that and find the midpoint somewhere down here. If we study this vertical region very carefully and try to find the point halfway through it, I believe we're going to get about 71 milliliters of sodium hydroxide added right about here. So we cut that in half. 71 divided by 2 is 35.5. So 35.5, this should be my midpoint. And that looks pretty good because this is indeed the flattest part of my pH curve where I have a perfect buffer where the pH is experiencing a very, very small decrease. So if I zoom in, try to get the pH at that point, looks to me like the pH at that point is going to be about 4.55. So if my pH was 4.55, then of course at the midpoint of a titration, you know that the pH equals the pKa. So my experimental pKa for acetic acid is 4.55. Now what we can do with this is actually look up the accepted value of the pKa for acetic acid. We can compare our results with that accepted value. So maybe we should call this the experimental pKa and the accepted value for the pKa. Some quick Googling reveals that it's about 4.76. So we're not that far off. But you know that saying we're not that far off, go away, is not good enough. We want to be specific, so we can calculate a percent error. And percent error is always going to be the experimental value minus the accepted value over the accepted value, and then of course times 100 to make it a percentage. So my experimental error is going to be 4.55 minus 4.76 divided by 4.76, which is about negative 4.4% error, and typically we like to be around 5-7% or less, so this is good. Why the negative sign? Well, it means that my experimental value was too low. But this is a pretty dang good titration, I would say. This has been successful. So experimentally, we have determined that the pKa of acetic acid is about 4.55, and you know that we could take that and we could turn it into the Ka, the acid dissociation constant for acetic acid, CH3COOH, dissociating, deprotonating to give off that acidic hydrogen ion. We could make we could calculate the Ka value for this. It's just going to be 10 to the negative 4.55, because once again the pKa is the negative log of the Ka. So if I have the pKa, I'm trying to go backwards, bring the negative sign over, raise 10 to the power of both sides, 10 to the negative 4.55, you guys can calculate that. That's going to be my experimental Ka value for this process. So you can see that we've been able to do a lot with titration. We can calculate unknown concentrations. We can find an unknown pKa value that equals the pH at the midpoint. Things like that.